Welcome to the fourth part of the scripting tutorial. From now on, these exercises will be conducted a bit differently. Over the course of the past 3 exercises, you should have gotten familiar with a big chunk of the most mundane actions, so you won't see me doing everything from scratch, as that would take forever. Instead, I will present you some prepared solutions or near final solutions, and I will explain their inner workings and point out and explain some intricacies. The goal of this exercise is to create something very close to a guard's behavior. A deaf and blind guard, but a guard behavior nonetheless. The first behavior will have the NPC going in circles indefinitely, and the other will pick a random point for each iteration of the loop. We will also add support for save and load to both of these behaviors. Let's get to it. First thing we're gonna need is a physical loop in the level, so let's place 4 tag points in there. You can copy a tag point with Ctrl+C. One disadvantage of this flat plane is the lack of any physical features, any reference point. The tag points are invisible in game mode, so we won't know for sure if the behaviors work fine. So let's use some brush. Geometrical entities can be manipulated and run their own Lua scripts, and vegetation can bend in the wind, and items can do their physicsy magic when you drop them. Brushes are just dumb, static 3D models. Let's use something vertical like columbarium. So we have tag point 1, tag point 2, tag point 3, and tag point 4. The first point will be our starting point, so I will use the columbarium to mark it. I will mark the other points with a smaller brush called bird feeder. Now we need to create a link network that defines the loop itself. So we will always say which point is the next one. Name the links NXT for next. You can edit the link name, if I haven't mentioned it already, by pressing F2. That's the same key used in Windows for renaming files and folders. Also, each time don't forget to cancel the target picking function by clicking the button again. Otherwise, you might introduce some unintentional links to the level. That's a very common mistake. That's it. Now we have our loop. And we need to enter the loop, so we need to find the first tag point. Create the same link from the NPC to tag point 1. This is all we will need for the level data so far for this first behavior. And now I will switch to our behavior holder, the smart area, where I already created some solutions. Here's the new petrol behavior with multiple solutions. This is solution 1, solution 2, solution 3, solution 4, and I will guide you through them. You might be interested in this comment box. They are created this way. Click comment box or write in a comment, and if you want to change the color, just hold down Ctrl and right click. So I can turn it green, stretch it, and so on. There are also comments for individual nodes. You can use this to organize and comment your code. So, solution 1. You can see that we have a loop. We search for something, we go there, then we wait, and then the loop repeats. What are we doing exactly? Imagine we are already on this point. We've reached it, and we want to go to the next one. We will search from this point along this NXT link, which will find us only one result, the tag point 2, and we can store it and go to it. Then we will find the third point the same way, and we will continue doing this in a loop indefinitely. There are multiple possible solutions. You can solve it using multiple variables, a dedicated init graph search, etc. And those would be fine, some would even be better readable, but this solution, with just one variable, one graph search and one move, is the most minimalist, but it's also a bit tricky. The first tricky part is the graph search. Again, imagine you are at the first tag point. You have it stored in this variable of type common width, and you search along the link and store the result in the same variable, so you overwrite it. Then you can proceed directly to the move using the overwritten value, which is tag point 2. And once you get there and wait, you search from tag point 2. You find the point 3 along the next link, and again you overwrite point 2 with point 3. And then you go to point 3, and on it goes. So that's the first trick, where you only use one variable and keep overwriting it, because you can always forget the last point, in this case. The other trick solves how to start the whole loop, how to get to the first point. That's why this expression is here. We will exploit the rest of our solution, which can already search from some entity along certain link. At the very start, the variable next point is empty, so the graph search would fail because of the missing origin. So what we'll do is that we will pretend the NPC is the initial next point and search from there. So we will store this ID in next point variable. This will cause that the first run of the graph search will find the first point, and then we can go to it, and then we are in the endless loop. So that's it. Let's see what it does. And it's clear I forgot to change which behavior the NPC is calling. Give me a second to fix it. So what about now? Yes, this looks promising. He got to the first checkpoint, and now he's in the loop. Good. Now I will use another feature. When you hold down Ctrl, you can use the numpad keys to mess with the speed of the simulation. Ctrl-, Ctrl+, and Ctrl-0 is basically everything you need. Plus speeds up the simulation, minus slows it down, and 0 works as pause and resume, and it always resumes to default speed. So now I will speed it up to see if he is indeed in an endless loop. So that's a success. I will pause it for now. Actually, I will speed it up a bit to get closer to him. Good. Pause again. So the solution 1 is successful. But guess what will happen when I save in this moment? Saves are created using Ctrl F5, and the simulation must not be paused, by the way. If I save and load at this instant, he will not go to the point 3 where he is headed now, but instead he will go to point 1. But why is that? You have to understand how saves work. The relevant information for this context is that we do not save the entire runtime state of brains, and we do not even save the variables by default. After loading, all brains are restarted, and it's your responsibility as a scripter to reconstruct the state of the brains as fast and as accurate as you can. To aid this process, we save all brain variables, which you can create in the brain panel. The scope of brain variables is such that they are accessible from any subbrain. You should not overuse them though. And we also save other variables which are marked as persistent, and that's what we're gonna use. But now we don't have any, so this next point variable will be erased. What will happen after loading is that he will go through this initial phase again, and he will find the first point. Let's try it. I also paused the program with F9 in order to look at the trees, so F9 again. So now speed it up a bit and Ctrl F5 to create save. Sorry for the check user interface. Believe me, this means that the save was indeed created. Now I can load it. This is slow because of this load simulation. And now you can see that he goes to the first tag point. This is functional, but wrong. The player expects that after loading, everybody just continues as though no save ever happened. So let's implement save and load support. Save and load is already prepared in this second solution. So I will just move this solution aside and bring this part home. You can move entire subtrees when you hold down Alt key and just move the parent node. As I said, all variables that are not persistent will be deleted, so we certainly need the next point variable to be saved, to be persistent. So all we need to do is just click this. And now you can see this indication here that next point is persistent. And there are also some other changes that I will explain to you. First thing is just a very simple test, an if condition. If condition node, of course, executes its child only when the condition is true. The syntax for these conditions is taken from Lua language. So this test prevents repetition of the initial expression if we already have something in the next variable. Say that we have this third point here. We don't want to overwrite it with this ID. How do you test if a common with variable is empty if it's uninitialized? Well, there's a global variable double_null which represents just that, so I can just compare the next point to the null value. So if the next point variable is empty, we are certainly in the short-lived initial phase and want this expression to be executed. Okay, on to the other difference. You might have noticed that in the previous solution, the graph search was first and this move group was second. So we first found the point and then we went to it. Now we have to do it in switched order. Why? Well, if we kept the order, then after loading, we would first start searching the next point from the point we had stored, a point we haven't even reached yet. So it's clear we first want to finish moving to whatever point was stored in next point prior to saving. So we'll go there, then we will wait, and only then we'll try to find the next destination. And the graph search is the same as this one. Last point. Why is there this test? Let's revisit saves. Saves are created as a request which pauses all AI brains in the world, and only after that happens, the save file is created. And this request can happen at any moment. It can happen in this moment, in this moment, or even in this moment between the expression and this loop. It is easier imagined what would happen if I add a wait here. Now we have more than enough time to request a save between the expression and the loop. You can test it yourself. If we had executed this entire initial script and then saved, we would have this ID in the next point variable. Upon loading, this if condition test would correctly skip the initial phase, but then we would attempt the move, a move to this ID. The NPC would actually try to move to himself. This particular script would survive this blunder. The move would just instantly succeed, but in a different script, we could be at risk of running into a truly dangerous situation. That's not what we want. So this other test skips this whole part if we saved in this very tiny and very unfortunate moment. And believe me, no dangerous moment is too short to be ignored. So we will skip the movement and move directly to the graph search to finally find the first tag point. Let's at last try this solution. And just a short speed up. Create a save. And now when I load, he should continue to this point. That looked fine. Now if I save again, he should go to the point 2. Cool, everything works. So now we know how to add a very simple support for save and load. That's a very crucial knowledge. We have 2 more solutions here. What are they about? They cover what's in the tutorial on Modding Wiki described in extras for this exercise. I will do them this time, partially, because you need some special knowledge to achieve them anyway. So these are alternative solutions. Instead of finding the next point each time we arrive to 1, basically running the graph search over and over again for eternity, we want to find all the tag points once, store them in an array, and then loop through that array. In this specific case, the first solution with save and load support is certainly better. But in some other scenarios that involve more complex setups, you might want to avoid executing too frequent graph searches. Non-trivial graph searches can get very costly in terms of performance demands. Instead, we will run just one more costly graph search and then use the much cheaper operation of stepping through array. Now we will no longer use this next point variable. Instead, we will use a variable called points. The type will be common with, and the form must be set to indexed. This will make it an array. So we will have the tag points stored in an array called points with numbered indexes starting with 0. Let's set up the graph search. We want to search from the MPC, so empty origin, and we want to go along the NXT links. And we need this new nodalizer node. Nodalizers are used for 2 actions. First, you use it to combine multiple filters. Imagine these filters have different link names in them. If there were an entity that is pointed to by these 3 different links from the origin, the nodalizer would find it. You just need to set the quantifier to exists and it combines the filters. This is also why you have to write in the child variable in the nodalizer here and not here in some filter. If there were more filters, each could have its own child, which would store the subresult of the single filter. And the second usage of nodalizer is that you can use the quantifier for all. It also combines the filters, but more crucially, it will append every result to an array, as opposed to filters, which can only return one result. Moreover, if there are more candidates, a filter will pick a random one. So we want to go along the NXT link, but we also need to go much further than just to the first tag point. We have to set the depth, which says how many jumps from the origin in this network are allowed. To get all the points we need, we have to go to depth 1, 2, 3, 4, not 5, because that would find the first tag point again and we'd end up with a duplicate result. Set depth, which is by default 1, to 4. You also need to set prune on find in the filter to false. If left set to true, it would prune the result and accept it from any subsequent substep of the search. So it would find the first point, store it in the array, and then it would not search from the first point because it was pruned. So we would end up with the first point only. The pruning functionality is there for safety and optimization reasons, but in this case it gets in our way. So we have to disable it. Now, after the search is done, we have the array points filled with 4 tag points. In the looped move, we can simply say that we want to move to the entity on the nth position in the array, and in the rest of the script, we will just manipulate the n. The n is represented by the variable index of type int for integer, and its init value is 0. Working with arrays is no different from C or Lua. You just use the square brackets to specify the array index. So points 0 is the first member of array, points 1 is the second, and so on. We will be reading the value of the actual array index from the variable index, so don't forget the $sign. In the first loop iteration, we go to the member points 0 and wait there. Then we will iterate the index by 1. You might recognize this syntactic sugar from C language. It's the same as writing index equals index plus 1. Although a more notoriously known equivalent, index plus plus, is not supported. Don't ask me why. So this will raise our index by 1. In the last step, we have to guard that we don't get out of bounds of the array. Our array will have indexes 0, 1, 2, 3, and its size will be 4. So we have to be sure that the index value we will be feeding to the move node does not get to value 4 or higher. Moving to, for example, points 4 would be a completely invalid request and we'd get an error. This condition is true if the index is equal to or higher than the size of the points array. This hash sign is our size of operator. So if it's true, if we get to the value 4 or higher by some magic, it means we got to the last tag point and we want to re-init the index value back to 0. Let's save it and test it. One last thing. We gotta set the index variable to persistent. Now this solution is safe load proof. That's all we needed. Let's jump in. Let's now pause and inspect the array. We have points members with indexes 0, 1, 2, 3. And they are tag point 1, tag point 2, tag point 3, tag point 4. And they are in perfect order thanks to the structure of the links. And our current index is 0 here. So unpause. Now we've just iterated and you can see that the index is now 1, so he goes to points 1, which is tag point 2. Let's observe the whole cycle. Okay, that seems to work just fine. Now let's test save and load. Also perfect. Good. So that's the third solution. Now let's have a look at the last one. The fourth solution is an extra bonus. It is almost identical to what you've just seen, but it works for loops of any size. Imagine you have an area which controls all the guards in town. It is also the starting point of several guard routes, where the guards can be sent, and each route consists of different number of tag points. Again, imagine that for whatever reason you need to process all these routes. Clearly, we wouldn't be able to use the third solution because we would need a different graph search depth for each route. So I will now mark the last point with a self-link named last. And we need to use graph search depth -1. Depth -1 is very dangerous, and ideally you should never use it. But for the sake of this exercise, we will take a look at it. Depth -1 search could result in a search going like this, and then being stuck in a loop and trying to create an infinite array. You can imagine how that would end. In short, you don't want that. What you want is this terminator self-link on point 4. There are multiple equally valid solutions to this problem, so take this one as just a mere suggestion. I've chosen it because it will also teach us something new and shed some light on certain quirks of these systems. So first, in the maximum depth, we will find the point marked as last and we will store it. Then we will do another graph search with depth -1. This one will go through the loop. It is almost the same graph search as we had in the previous solution. So, together with the nodalizer, this search says, if it's linked by nxt-link and it's not the last point, then append it to the array. Since it will run to no results after the third point, it will stop there. However, this will only add the points 1, 2, 3 in the array. We need one extra step, and that is appending the last point to the array. This is done by a var operation node with the operation pushback. Var operation node requires specific syntax for some of the operations, so yeah, you need to write in the last point variable in parentheses like this. The rest of the script is the same as here. So that's it, we can test it. Before I test it, I will add some breakpoints. You can apply breakpoints to a node and its subtree by holding down Shift and double-clicking. Otherwise, a breakpoint is added to a single node in the context menu over an input port. Now when I save this tree, they are baked in, but you can also add them in runtime. And you also need to press F7 to turn on breakpoint debug mode, which is indicated by this orange color here. So have the MPC entity selected and jump in. Now the script paused at the first breakpoint. You step through using F5. Let's watch this autos panel here. F5. Did we find the last point? Yes, it's tag point 4. Now we should find points 1, 2, 3. Good. Now the point 4 should be added. Yes, 1, 2, 3, 4. F5. And now he moves as in the previous solution. Good. The support for save and load is the same, so I don't need to run this test. So that's the looped patrol behavior with 4 different solutions. Let's move on to the randomized behavior. But first, we need to quickly prepare the links for it. Just link each point with a link named RND for random. And one thing I completely forgot. We added these brushes into the level like 30 minutes ago, but navmesh stayed the same. This might cause slight problems as the NPC cannot see them. Now there are proper holes and the NPC knows where to go. Or rather, where not to. Save the level. So now the NPC can find each point independently. I already have the random patrol behavior prepared. The random patrol behavior sends the NPC to a random point, and then selects a different random point, that is any other than the one where he's standing right now. The behavior would survive if you send an NPC to the same point twice. The move would just instantly succeed. But we want to be pünktlich, right? We have two variables. The random point, that's where the NPC moves, and previous point. This will help us exclude the point we are standing on. Both variables are single and common width. There are no arrays this time. So what do? If we have no random point, we run a graph search. We search from this ID, the NPC. And we want to exclude the previous point, along the tag RND. That is the point where we are standing right now. And since we don't want an array now, we use Nodalizer with the exists quantifier. The result is stored in a random point. Now the easy part, we just go there and wait. Once we get there, we want to copy the current random point to the previous point variable. And then we want to erase the random point variable. This will signalize that we are ready for another search. If random point is null, which it is by default, the if condition will be true once the loop starts anew and the search will happen. If it isn't null, it means that we saved and loaded and the NPC has not reached its destination yet. We didn't finish this part. So we will skip the search and go directly to the move part. And then there's also this other node called Atomic Decorator. It creates what is called atomic context. All action-performing nodes are executed in two ways. The first type is started, then they are continually executed, and then they end. These are called timed nodes, and they are indicated by this clock icon here. They usually wait for something, a message to be sent, a state to be changed, or an animation to be finished. Other nodes are executed in one go, in one tick of the AI engine. These are called instant or non-timed nodes. They are inherently atomic. Even if you had an expression node with, say, 100 different operations in it, all or none of them are guaranteed to be performed. Atomicity is closely related to the save and load issue we already tackled in this exercise. Remember, a save can be requested at any moment, and this leads to all AI to be halted. This halt waits for all atoms to finish their job, and only then it can save. Atomic Decorator allows you to combine several instant nodes and defines the whole set as one logical atom. So you cannot save here. If the save is requested in this moment, the system will wait until this whole content of the decorator has succeeded. So these nodes are now guaranteed to be executed together. And that's what we need, because we don't want to copy the random point to previous point and then not reinitialize the random point. That would lead to an undefined state and the behavior might, misbehave. I repeat, the nodes must be instant, You cannot add a timed node under atomic context. That would produce an error. I'll just change the call behavior here. And we maybe want to step through first. So jump in. I didn't have him selected, so the first breakpoints were skipped. Shouldn't matter. So what have we found? We found a random point. It's the point 2, and he went there and waited. Now he's gonna perform this atomic sequence. So now the point 2 is in previous point. And then he erased the random point. So the loop ends and repeats. Now this if should let us find another point that isn't the previous point, the point 2. So we found number 4. Now he should go there. Oh my god, Henry, what have you done? You almost died for this. Okay, the player should be protected from fall damage, but this script breaks sometimes. I don't know why, to be honest. So this clearly works, and I will now try the script again. Oh, sorry, the breakpoints are still there. Just remove them with Shift and right click. Oh no, not again, Henry. Where have you lost your protection, dude? Anyway, let's try the save load. It would be best if he moved back. Yeah, now. Save. Now load. Oh, breakpoints again. Now he should go to point 2. Well, that's a wrap up. You have successfully finished the 4th exercise. Well done. See you next time.